Ships can't climb hills. They have no wheels, no legs, no way to gain elevation. A river that drops 15 meters is, for a loaded barge, a dead end. And yet, for 400 years, boats have been climbing hills every day on every working canal on Earth using nothing but gravity, 2 wooden gates, and a box of water. Dutch canal engineers had the basic chamber concept by the 1400s, but it was a hydraulic engineer named Leonardo da Vinci working on the Milan Canal system in 1497 who refined the gate geometry that made it work reliably. The engineering problem was precise. 2 stretches of water at different heights. 1 loaded barge, 30 tons, 12 meters of elevation, no engine, no crane. How do you lift it? Canal builders in 16th century Europe faced a hard physical constraint. Natural waterways aren't flat. They drop, they cascade. A loaded barge needs a water surface level enough to float. You can't push 30 tons uphill through a current. Early engineers could route around low hills, but that detour added weeks to every journey. Beyond a certain elevation, you simply couldn't build canals through hilly terrain at all. What they needed was a way to step the canal up, like a staircase. Move a boat from the lower stretch to the upper stretch using as little water as possible with no power source. The water budget mattered as much as the mechanism. Every liter used to lift a barge was drained from the upper canal. Use too much and you lower the whole route. The system had to be nearly closed, lifting a boat without bleeding the waterway dry. The first solution was called the flash lock. The concept was simple. 1 gate across the river. Close it and the water backs up on the upstream side. When the level is high enough, you open the gate and the boat rides the rush of water through. It worked, barely. A typical flash released a wall of water violent enough to capsize a lightly loaded barge. Getting upstream was worse. You had to haul the boat through the surge by rope against the current meter by meter. And every time you opened the gate, you drained weeks of accumulated water in minutes. In the driest months, a single flash could lower the channel enough to ground every barge on the route for days. Engineers needed to trap the water, not throw it away. The logical step was 2 gates with a chamber between them. The pound lock was the right idea. 2 gates, a sealed chamber. You could raise or lower the water inside the chamber independently, and in theory, float the boat up with it. The problem were the gates. A flat gate at the bottom of a 12-meter water column faces roughly 6 tons of pressure per square meter. To open it, you have to swing it sideways against that force. The hinges bent, the seals leaked, the wood warped under the load. Once the gate started to fail, the water pressure made it fail faster. Every crack let more water through. Every leak widened the gap. The very force the gate was supposed to hold was the force destroying it. Engineers tried iron-reinforced hinges, heavier timber, different frame geometries. Nothing worked beyond 10 meters of head pressure. The physics were unforgiving. Double the water depth, the force at the gate base quadruples. A 12-meter column wasn't twice as hard to resist, it was 4 times worse. For decades, the flat gate lock was the weakest link in every canal system. The engineering problem wasn't the chamber, it was that every gate design was fighting the water, and the water always won. The breakthrough came from geometry. Instead of a flat gate fighting the water head-on, engineers angled 2 gate leaves into a V pointing upstream. When water pressure hit the angled face, the force split. One component drove straight into the hinge, absorbed. The other drove the 2 leaves harder together at the center joint, tightening the seal. The Mitre gate turned the enemy into the mechanism. The greater the water pressure, the harder the gate sealed. The angle isn't arbitrary. The V must fall between roughly 120 and 140 degrees to function correctly. Too shallow, and the lateral component pushes the leaves past each other. Too deep, and the gates can't clear the chamber walls to open. The geometry is the engineering. Leonardo da Vinci documented and refined this geometry for the Milan Canal system in 1497. It is, in engineering terms, one of the most elegant self-sealing structures ever built. Here is how the complete lock cycle works. First, the lock keeper opens the small sluice paddles built into the lower gate. Not the main gate, just small openings, perhaps 30 centimeters across. Water flows between the chamber and the lower canal until the levels match exactly. Zero pressure difference across the gate. With no pressure differential, two people can swing the miter leaves open by hand. The barge enters the chamber. The lower gate closes behind the barge. The chamber is now a sealed box of water, isolated at the lower level. The lock keeper opens only the upper sluice paddles. Water from the upper canal flows into the chamber through these small openings, not because of any pump, because the upper canal is higher. Gravity pulls it in. The sluice opening is small by design. A large, sudden opening would create turbulence violent enough to surge the barge sideways into the stone walls. The small paddle controls the fill rate and keeps a 30-ton hull from becoming a battering ram. The chamber fills slowly, 15 to 20 minutes for a 12-meter rise. The sluice paddles control the flow, keeping the water surface calm enough that the barge doesn't surge against the walls. When the chamber reaches the upper canal, the lock keeper closes the sluice paddles. Both sides of the upper gate now hold identical water levels, zero pressure differential. One lock cycle has used exactly one chamber's worth of water, drawn from the upper canal. That's roughly 1,000 cubic meters, transferred downhill, not wasted. The upper miter gates swing open, same principle as before. No pressure, no resistance. The barge moves forward into the upper canal, 12 meters higher than where it started. One chamber's worth of water used, and nothing more.
By the 1760s, Britain had a logistics crisis. Moving raw materials over land was slow and ruinously expensive. A horse on a good road could pull 1 ton. The same horse on a canal towpath could pull 50 times the load at half the speed, but the journey now took days, not weeks. The Bridgewater Canal, completed in 1761, connecting coal mines at Worsley to Manchester, used canal locks to handle the terrain. It immediately halved the price of coal in the city. Within 30 years, Britain had over 4,000 kilometers of navigable canal, and the lock, specifically the Mitre Gate lock, made every kilometer of it possible. The Industrial Revolution didn't move on roads, it moved on water. At peak canal operation, a single busy lock might work 40 boats in a day. Each one climbed the hill on nothing but the water already in the upper reach, no fuel, no machinery, no power source beyond gravity. The Panama Canal's lock gates are made of steel, weigh 700 tons each, and stand over 20 meters tall. They open on exactly the same principle. Sluice paddles first, equalize the levels, zero pressure differential, then swing. The next time you cross a canal, look for the angle of the gates. That V, pointing into the current, is the same geometry ships have been climbing on for 500 years.